Hey guys, welcome back. Gonna do a video for you today about our first kind of big application of derivative and related rates is what it's called. And while related rates can sometimes be tricky, I'm gonna try and break it down for you in a way that hopefully helps you with what I think is the hardest part, or what a lot of first years think is the hardest part, and that is how do you set these darn things up? And so that's what we're going to start with. Take a look at an example or two, and then hopefully it'll start to make some sense. I'm going to take you through a few of the classics as well. There are some related rate problems. They're just in every single calculus book, and they just seem to show up all the time. So let's start off by taking a look at what the heck we're even talking about today. And so related rates. And so what we're talking about are rates of change. Okay, now in calculus, right, when we hear the words rates of change, we need to be thinking, okay, that means derivative. When we hear the word slope, we need to be thinking that means derivative. So when we hear derivative, we should be thinking derivative, but of course that one's pretty obvious. And so what I want you to think about today, or at least to start off with, is imagine, if you will, a pool of perfectly calm water. Okay, so nice, calm, idyllic sort of pond. And then we drop a rock that disturbs the surface of the water. Okay, so the rock will go in and it'll create a series of concentric circles. Oops. And these ripples, as they go further and further out, okay, you can imagine, right? They all started with that stone that landed, right here in the middle of this whole thing. And so what I want to think about is the area of the disturbed water. Okay, so imagine from the center of where we drop that out to the edge of the largest circle. Okay, there's a radius there. And so in a related rate sort of scenario, what we might be thinking is like, well, okay, how does the rate of change of the area relate to the rate of change of the radius? Okay, so if we think about it this way, if I drop the pebble into the calm water, and I might ask myself, okay, what is the rate of change, okay, of the area of the disturbed water okay, when the radius is 4 feet and the radius increases at a rate of 1 foot. That's a foot per second. Okay. Question. There we go. So what is the rate of change of the area of disturbed water when the radius is 4 feet and the radius increases at a rate of 1 foot per second? So let me think about this for a minute. How do I relate area to radius for a circle? Well, area is equal to pi r squared, of course. And what are they asking me to find? The rate of change of the area, rate of change of the area. Okay, so that's the derivative of area. Okay, but notice in this case, the rate of change of the radius was given at 1 foot per second, right? Oh, that's feet over seconds. So radius is actually some function of time. Makes sense? There is an implication here that the radius is actually a function of time. That's why it's an implicit derivative. You see, they want me to find the rate of change of the area, but they wanted it over time, right? dA dt, not dA dr, okay? We're not looking for the rate of change of area with respect to radius. We're looking at the rate of change of area with respect to time. Okay, so that's the quantity we want to know. Oops. Okay. What do we know? We know we want that when the radius is equal to 4 and the rate of change of the radius is equal to 1 foot per second. Now, this is where related rates gets a little tricky, okay? Because if I were to put 4 in now, before I do any deriving, okay, then I would have a equals 16 pi, okay? That's a constant. So when we derive it, what happens is it goes to 0, right? Okay, so by putting in a constant in place of a variable before you derive, you freeze it in time, okay? It's suddenly frozen in time. Okay, and remember, calculus is all about the mathematics of change. And so we want to actually let R be changing over time. So when I go to take my derivative here, I have to do so implicitly with respect to time. Well, on the left-hand side, that's pretty easy because the derivative of a to the first power is 1 times the derivative of a with respect to time. It's implied to be a function of time, so d dt. Now over here on the right-hand side, pi is a constant. So I'm going to move it over. Now I'm going to take the derivative of r squared, which is 2r to the first. Okay, but then according to the chain rule, because we have the implication that r is a function of time, we must multiply by dr dt. Now we can plug in everything that we know, and we'll get that dA dt is equal to, well, 2 times r, which is 4, times 1, so that's 8 pi. Now here's what I want you to think about. The units on the radius are feet, right? The units on dr dt are feet per second. What happens when you multiply feet times feet per second? That's right, you get square feet per second. And that sort of makes sense, right? The units should work out. That old dimensional analysis thing that you did back in science class with Mr. Baker or Ms. Herc or Mr. Wright or whoever, yeah, it comes into play here too in calculus. When we're doing related rate problems, because these are actual physical quantities, okay, the units should work out. And so there's a great example of a related rate problem. Okay. Let's try another one. See if we can come up with a relationship for this one. We are inflating a spherical balloon. So now we have a balloon that's a perfect sphere. Okay, I know most balloons are not perfect spheres. Okay, but we'll do our best here to have a perfectly spherical balloon. Okay. Oops, that's not very good. The pen slipped across the thing there. There we go. There's our spherical balloon. Okay, and inside our spherical balloon, we have a radius r. Okay. And this time, what I'm told is that the spherical balloon is being inflated at a rate of 4.5 cubic feet per minute. 4.5 cubic feet per minute. Does that sound like the rate of change of cubic feet per minute? That's a change of volume. That's right. See how I did that? I figured out by the units, cubic feet. That had to be volume. Okay. This time, they want us to do a different question. They want to know, well, how fast is the radius changing? Okay. What is dr dt, right? When r is equal to 2 feet. Well, here I have dv. Here I'm trying to find dr. I'm given r. Is there some way to relate the rates of change of v and r in a sphere? Well, of course there is. Okay, you know the equation for the volume of a sphere, I hope. 4/3 pi r cubed. And so again, I'm using that known geometric figure relationship here to say, well, okay, so then if that's the relationship for volume and radius, when I derive it then with respect to time, okay, well, 4/3 and pi, those are just constants. So now I just multiply by the derivative of r cubed, which is of course 3r squared. But r is implied to be a function of time. So the chain rule says you're not done. You have to multiply by dr dt. Excellent. Well, notice in this case, dv dt was given, right? So that's where the 4.5 or 9/2 is going to go. Okay. R is said to be 2 in this case. So I have 4/3 pi times 3 times 2 squared. dr dt. Okay, just plugging in the 2 right here, goes right in there. Okay, you square it, you get 4 times 3 is 12. Okay, and then notice that the 3 would cancel here, right? And so we get 16 pi dr dt. So just divide by 16 pi to the other side. And there's your dr dt. dr dt is, what is that? 9/32 pi. Okay, that's approximately 0.09. And now let's think about this. I had cubic feet per minute in the numerator, right? I divided by, well, let's see, I had r squared when I did this. So that must be square feet, right? So cubic feet per minute divided by square feet. Yep, you get feet per minute. So 0.09 foot per minute. And yeah, there you go. The units worked out again. Oh my gosh. What are the chances? Yeah, there's just a lot of different ways that we could go about relating these rates as we go through. Okay, and I'm going to give you a couple of the more common ones now. Okay, so let me show you. When you get a related rate problem, okay, there are a few common actors or common problems. So, oops, sorry. Common relationships that we might try when we're doing a related rate problem. One of them, as you just saw, was known geometric figures. Circles, spheres, cones, cubes, rectangular prisms, whatever, some kind of a known geometric shape that we kind of know how to relate the sides or the slant height of a cone or the radius of a sphere, whatever. Could be a known geometric figure. One that shows up all the time. A Pythagorean relationship. Now, also remember that we used Pythagoras' theorem to create something called the distance formula back in geometry, right? Okay, so known geometric figures, yes, but also remember Pythagorean theorem, because that's also the distance formula. That shows up quite a bit. Another one, SOHCAHTOA. Okay. Yeah, trig shows up in these things a lot, especially when they have questions about angles and how does this angle change. And so we'll see some SOHCAHTOA relationships that we're going to want to work through. And then the last one that we sometimes will use, similar triangles. A lot of times a related rate problem comes down to a similar triangle question. As we work through a few more examples here, my first two were definitely known geometrics, right? We had a circle, right? We started with a circle idea, and sure enough, we use the area of a circle. That's a formula from geometry we know pretty well. We use the volume of a sphere. Sure, no problem. Now let's get into some of the ones, and I would say this next one is what I would call a classic. Okay, it's in every calculus book in the world, pretty much. So, what I want you to picture is a house. Here's a house. Okay, and here's the ground. Okay, and you have a ladder leaning up against the side of the house. Okay, so we have a ladder here. It's leaning up against the side of the house. And my ladder is, of course, there we go, making a right triangle. Let's make sure it's touching the wall of the house. There we go. And so my ladder is 25 feet long. Okay, 25 feet. And actually, you know what? That looks like a derivative symbol from Newton's notation. So I'm going to go 25 feet. Okay, and the base of the ladder is 7 feet from the base of the house. So we've got a 7 foot distance here, down at the bottom. Right here, that's 7 feet. Okay. And your buddy thinks it'll be hilarious to pull the bottom of the ladder away from the wall. Okay, ha ha ha. Not so much fun if you're actually on this ladder. But we're going to pull the base of the ladder away from the wall at 2 feet per second. Okay. And my question for you is, how fast is the top of the ladder sliding down the wall at this particular instant in time? Okay. Supposed to be an S in there. Let me try again. There we go. First time I've said how fart. Not appropriate. All right. Let's see. How can we relate all of the stuff that's going on in this triangle? Are you thinking known geometric? Sort of. Or are you thinking Pythagorean relationship? Definitely Pythagorean relationship, right? Now, here's my question to you. This side of the triangle down here, that's 7 feet, but changing, right? We need to give it a name. I don't know what name you chose. I chose A. Okay. This vertical side of the triangle up the wall, right? How fast is that side changing? I need to give it a name. I'm going to call it B. And the length of the ladder, well, let's call it C. So my relationship then is, yes, the Pythagorean relationship. A squared plus B squared equals C squared. Now, I want you to remember what I said earlier about sides that are changing versus sides that are not changing, okay? Because if we were to accidentally sub in a value before we derive, we freeze things in time, right? So which one of these isn't actually changing though? C, right? Yeah, C is staying at a constant 25. So before I derive, it's okay to put C in. Okay. Now, if you don't want to ever make a mistake on this, you're like, I'm just not going to substitute in because I don't want to screw that up. Then what would dc dt actually look like, right? Oh, it would be 0, right? It's not changing. So it's okay if you don't do it. It's just I worry about, ending up with trying to derive that and then messing it up. Now, B is definitely changing, right? So we're going to call that dB dt. So what are we going to call this 2 feet per second? Well, that's the change in A, right? So that's going to be dA dt. And so really we have everything we need, right? Oh, wait, we don't have how long B is right now. Now, B is changing, but it has got a length right now. And if you've already done the Pythagorean theorem in your head, you recognize that this is the infamous 7, 24, 25 right triangle. Okay, but I can't use the 24 yet because I haven't derived anything yet. So let's take our derivative. I'm going to get 2a dA dt plus 2b dB dt equals 0. Because remember, if I took its derivative, right, I'd get 2c dc dt. But we know c is not changing, so it's going to equal 0. Now we're ready to just plug in everything we know. I've got a, which is 7, dA dt, which is 2, b, which is 24, dB dt, which is my unknown. Well, check it out, guys. If I take the 2 times 7 times 2, which is 28, and move it to the other side, okay, I'm going to get 48 dB dt equals negative 28. And then I'll divide both sides by 48. And notice dB dt, right, is negative. Now, what goes into 28 and into 48? 4 does, right? And why is it negative? Why is dB dt a negative number? Okay, have you figured it out yet? What's happening to the length of side B? It's getting shorter, right? B is 24 feet right now, but it's getting smaller, so its rate of change is negative. Okay, dA dt was positive. Why? Because the side A was getting longer. It's 7 feet now, but it's going to get longer. Okay, so the sign of your rate of change is important. Okay, it makes a big difference. Okay, the ladder sliding down the wall of a house problem is a classic. It sets up all the time with feet. It's nice because you can do it in meters as well, because you just make the ladder 5 meters long, and make A like 3 meters from the base of the house. Then you got a 3, 4, 5. So there's lots of things we can do with the ladder sliding down the house problem. It's another one of the classics. All right. I don't want to get too far into this or make this video too long, but I do want to show you one of the trig ones. Okay, and what I'm going to do is I'm going to do a continuation of this problem. Okay, so what I'm going to do is I'm going to mark an angle theta in our drawing here. And my next question, okay, here's angle theta right here, is can we find the rate of change of theta in this same situation? Okay, so that answer is yes. Let's see here. I thought there was a way to copy this. Apparently not. So I'm going to have to just clear some of this off of here. So the setup is the same. Okay. So we've got the same. Oh my! I didn't mean to erase the list of choices there. Oh well, it's too late now. Apparently that's done. So we already know what's going to happen here. So I told you earlier, when they bring in the angle, it's probably going to be the SOHCAHTOA ones. So let's clear some of this out of here. All right. So this time, the question is, what is the rate of change of the angle theta? In other words, we want to solve this for d theta dt. Well, now we come back to how can we relate theta and its rate of change to the triangle that we have? Okay, and it's a right triangle, so some right triangle trigonometry makes sense. The question I have for you is which angle or which ratio should we use? Okay, because there's three to choose from. Okay, we could use sine, we could use cosine, we could use tangent. I'm going to rule out tangent right away because here's why. Both sides of the triangle that tangent needs are changing, right? The opposite side and the adjacent side over here, they're changing. I'd rather only deal with one rate of change. How about you? Right? So it makes sense to not use tangent. And which one should we use? I'm going to use sine. And the reason I'm going to use sine, guys, is that is the opposite over the hypotenuse. Or the way I have my triangle labeled, that's A over C. And the reason I used A was that was the given side. Everything I did for B was calculated. And honestly, I don't want to use that -7/12 rate of change for it. So I'd rather use the +2 anyway. So that's why I'm going to go ahead and use the sine. So let's do this. Let's take our derivative. Now I'm sorry, let me write out the equation a little better here. I've got sine of theta equals 1/25 times A. If you want, you can move the 25 over to the other side, make it 25 sine theta equals A. I don't care. The calculus will work out the same no matter what. Okay, so here's what we're going to do. We're going to take our derivative. Now on the left-hand side, remember, it's theta dt. So theta is implied to be a function of time. So the chain rule is going to kick in. I'm going to get cosine of theta. Okay, that's taking the derivative of the outside function, times the derivative of theta, d theta dt, equals 1/25 is a constant, times the derivative of A. That's just 1. But then remember, A is also a function of time. So we get dA dt over here. And everything we have in here, we either know or it's what we're trying to find. Do we know the cosine of theta right now? Yes, we do. Okay, it's 24/25. It's adjacent over hypotenuse. So this is 24/25. We don't know d theta dt. That's what we're supposed to be finding, so that's okay. And dA dt we know is 2. Like that? Yeah, it works out great. Okay, well, let's solve for d theta dt. How do we get rid of this 24/25? We multiply by 25/24 on both sides. And these guys cancel. And over here on the, let me grab a different color here. Over here on the right-hand side, look, the 25 cancels. The 2 over 24 cancels. And we get 1/12. And in calculus, we are always in radians. So we get 1/25 radians per second. Or sorry, 1/25. I'm sorry, I misspoke. I was trying to make the image bigger. 1/12 radians per second. So that's how you could use a trig ratio to solve a related rate problem. So now we've seen 4, right? We've seen known geometric circle. We've seen known geometric sphere. We saw the Pythagorean theorem one, okay? And now we've just seen a trig ratio one. The similar triangles one is a little bit different. We're going to save that one for next week. And when we take a look at the Shadow Man problem. So yes, Shadow Man, I know it seems like we should have done that around Halloween. It's very creepy sounding. But Shadow Man is just another kind of related rate problem, and it does use similar triangles. So thanks for watching, guys. That is it for me on related rates. Just a reminder that each week. We will normally have videos for you each class. I know it was a little different at the beginning of this week. Um, that was just a little bit different with implicit derivatives. So hopefully you found this video useful, and thanks a lot for watching, guys. I'll see you next time. Bye-bye.